Hello, I am Dr. Imran Khan, and today we are going to discuss microcomputer architecture design. Due to technological advancement in integrated circuits, it is now possible to put the controller, also called a sequencer circuit, and data operator in a single silicon chip. Such a combination of data operator and controller is called a microprocessor. If a memory, input-output modules, and a clock circuits are added to a microprocessor, the result is a microcomputer. There are five basic units of a microcomputer: input unit, memory unit, arithmetic logic unit, control unit, and output unit. So in today's lecture, we are going to discuss microcomputer architecture in details. Outline. First, we will discuss technology trends in computer design. Then we will discuss computer architecture, performance of computers, and as an example, we will discuss MIPS architecture and MIPS single cycle implementation. Technology trends. Processors have undergone a tremendous evolution throughout their history. A key milestone in this evolution was the introduction of the microprocessor. A microprocessor is implemented in a single chip. The first microprocessor was introduced by Intel under the name of Intel 4004 in 1971. It contained about 2300 transistors. It was clocked at 740 kHz and delivered 92,000 instructions per second, while dissipating around zero point 0.5 watts. Since then, every year we have witnessed the launch of a new microprocessor, delivering significant performance improvement over the previous ones. Some studies have estimated this growth to be exponential, in order of about 50% per year, which results in cumulative growth of over 3 orders of magnitude in a time span of 2 decades. These improvements have been fueled by advances in manufacturing process and innovation in process architecture design. So the technology trends in microprocessor design includes the number of transistors are continually increasing. Transistor count per chip grows by 40 to 55% every year. Logic gate delays improve faster than wire delays. Chip cost increases rapidly with chip size. So that's why we are interested to have the smaller transistors. Processor performance improve faster than the memory performance. So the bandwidth improvement with scaling. Nowadays, power dissipation is a major limitation in microprocessor technology, because we already know that uh, nowadays we have billions of transistor over in small silicon areas, and each transistor is dissipating power. So that's why power dissipation is a major limitation in today's technology. So here we have the architectures of two computers. First one is the ENIAC. It was developed in 1946. So here you can see, and a smaller computer that was developed by IBM in 2007. it's a very small chip, you can see. So you can see uh, there is a tremendous evolution in microprocessor technology. So here, if you see, this is the ENIAC computer, electronic numerical integrator and computer. ENIAC was the reprogrammable digital computer. It was built in 1946 to calculate artillery firing tables of US Army. This huge device had 17,468 vacuum tubes, 1,500 relays, 70,000 resistors, 10,000 capacitors, and consumed almost 150 kilowatt of power. ENIAC was able to store a maximum of 20 10-digit decimal numbers and could discriminate the sign of a number, compare quantities for equality, add, subtract, multiply, divide and extract square roots. So with the revolution in transistor technology, we are continually scaling down our transistor, and also with the time the vacuum tubes which we used in the design of ENIAC was replaced by the transistors, and now we can put billions of transistors in small silicon chips. So that's why IBM was able to uh, manufacture this IBM Power PC in 2007, and so it can perform 10 billion operations per second. So you can see the area is around 1 centimeter, and if you see this any computer, its area is around 10 meter. So if you see here, this small chip is millions time faster than this bigger computer, and also it is millions time faster uh, and the smaller, efficient, and it has much less power dissipation, and it can perform much more. And even today, we have a lot of good microprocessors which can perform even much better than this. So even nowadays in our mobile phones, we have around 15 billion transistor in small silicon area. So Moore's law. So in 1960s, Gordon Moore noted that the semiconductor industry doubled its effectiveness uh, after every 18 to 24 months. So this Moore's law was a prediction by Gordon Moore, and so we already know that the transistors can be used to increase the processor throughput. Theoretically, doubling the number of transistors in a chip provide it with the capability of performing twice the number of functions in the same time and increasing its storage by a factor of 2. So here you can see that the trend in the number of years and the number of transistors and uh, the processor technology. So this graph is showing the relationship between these microprocessors and number of transistors. So here you can see that nowadays, if you compare the microprocessors of 1970s and 80s, and if you compare the processors of year 2020, you will see that now we have much powerful microprocessors, much smaller, much powerful microprocessor that can perform extremely well compared to our previous microprocessors. So the computer architecture. In computer engineering, computer architecture is a set of rules and methods that describe the functionality, organization, and implementation of computer system. Some definitions of architecture define it as describing the capabilities and programming model of computer, but not a particular implementation. In other definitions, computer architecture involves instruction set architecture design, microarchitecture design, logic design, and implementation. So here you can see the block level diagram. So here you can see that here we have this establishment of functional interface to the software, and uh, after this we have this hardware, basically computational structure. These computational structure is the hardware, and if you see at the bottom level, you will see uh, an ocean of ultra fast transistors. Okay, because we already know that nowadays all the functionalities, all microprocessor, and everything we can design with the help of MOSFETs. So here, this is the block level diagram uh, of a basic microcomputer with the central processing unit. So here, black lines indicate data flow, and whereas the red lines indicate control flow. Here you can see, and the arrows indicate the direction of flow. So here you can see we have this central processing unit, and inside this central processing unit we have this control unit, different type of registers, combinational logic circuits. Okay, so here you can see we have these input devices, output devices, and this is the memory unit. So this is the basic architecture of the microcomputer. Okay, so instruction set architecture. An instruction set or instruction set architecture, ISA, is a part of computer architecture related to programming, including the native data types, instruction registers, addressing modes, memory architecture, interrupts, and exception handling, and external input output modules. So here we have the table for our MIPS 64 instruction set architecture, and here you can see the programmer's view, basically the contract between software designer and the computer designers. Okay, so these are a few points need to know as a software and the hardware engineer, like the rules of the registers, memory addressing, data types, operation types, control flow, instructions representation. And here, if you see the MIPS 64 instruction set architecture, so it's basically reduced instruction set architecture. Okay, so this RISC stands for reduced instruction set architecture. So it has load, store, general purpose registers, the architecture. So it has 32 integer plus 32 floating point registers. So it has different types like 8 bit, 16 bit, 32 bit, and 64 bit integers and floating point data types. So this is basically a 32 bit instruction set architecture. Okay, so the let's discuss the goals of computer design. The most common goal in computer architecture revolve around the trade-off between cost and performance. The performance, we can say the speed of your microprocessor. The other factor or other considerations may include size, weight, reliability, feature set. and power consumption. So the most important goals of computer designs are the functional requirement, uh, basically the software based, and the interaction uh, requirements, resource constraints, dependability, performance, or cost per performance. So these are the most important goals of the computer design. So system buses are used to communicate between a microprocessor and different devices like input devices, output devices, and the memory unit. So here you can see we have the buses that are used to connect input output devices and memory units with the microprocessors. So here you can see the microprocessor. So it is connected to the different input devices, output devices, and the memory unit. So we have three different type of buses: data buses, address buses, and the control buses. So these system buses we already discussed in our previous lecture. So if you have any problem, please go to our previous lecture. Architectural consideration. For n-bit microprocessor, we should have n-bit ALU or arithmetic logic unit, registers, buses, memory, data interface. So nowadays, the embedded microprocessors, they are usually 8-bit, 16-bit, and 32-bit. So for desktop computers or the servers, we have 32-bit or even 64-bit systems. And nowadays, even people are working on the 128-bit systems. So basically, the computer size determines the address space. So here you can see this is the basic architecture of the general purpose microprocessor. So here you can see we have this control unit. This is a program counter and the instruction register. So here you can see we have the interface with the memory. So here we have this control buses and the interface to this ALU or arithmetic logic unit. And here we have this different types of registers. So basically, the PC size determines the address space. So now we will discuss MIPS microprocessor without interlocked pipelining stages architecture. So MIPS, basically MIPS is an abbreviation of microprocessor without interlocked pipelining stages. So MIPS is a reduced instruction set computer. We also call it RISC. Uh, so it's instruction set architecture, ISA, developed by MIPS technologies. So the early MIPS architectures were 32-bit, but nowadays we also have 62-bit architectures. OR instructions are used when all the data values used by instructions are located in the register. OR type instructions have the following format. So this OP, RD, RS. So this is the format. So this OP is instruction operand, RS is first register source operand, RT is second register source operand, RD is registered destination operand. So this is basically the meaning of these different mnemonics. So here you can see this is the format for the instruction set of the MIPS microprocessors. So This we call it the instruction set format. So here you can see this is the opcode, RS register, RT register, RD register, and here we have this shift command and this additional operands. Okay, FUNCT. So we are going to discuss it. So this opcode opcode is basically the machine code representation of instruction mnemonics. So several related instructions can have same opcode. So this RS, RT, RD we already discussed in the previous slide. So these are the representation of source and the destination registers. So this shift or this SHMT, this is the command used for used with the shift and the rotate instructions. So this is the amount by which the source operand RS is rotated or shifted. So these FUNCT, this is the additional opcodes. So these are used for the instructions that share an opcode. The FUNCT or parameter contains the necessary control codes to differentiate the different instructions. So instruction execution in the MIPS processor. So we have different steps of instruction execution. So we are going to discuss here in this slide. So for each instruction, we have this instruction fetch, instruction decode, operand fetch, execute, computation, memory access, and write back results to the registers. So now we will discuss the MIPS single cycle implementation. Single cycle means that all implemented instructions complete in exactly one cycle. To achieve this, the cycle time is the inverse of clock rate, is set long enough that the slowest of the implemented instructions have enough time to complete. So this is basically the hardware for the instruction fetch code. So how we can do it? So we will discuss it here. Okay, so here we have different hardware. So here you can see we have this instruction memory, this PC is the program counter, and here we have this adder. So how we can do it? This instruction memory to start. First, we have this instruction memory. So instruction memory is a state element that provides read access to instruction of a program, and given an address as input, supplies the corresponding instruction as that address. So this is the purpose of instruction memory. So next we have this program counter or the PC. The PC is also a state element that holds the address of current instruction. Essentially, it is just a 32-bit register which holds the instruction address and is updated at the end of every clock cycle. And in the end, we have this adder. The adder is responsible for incrementing the PC or program counter, this program counter, to hold the address of next instruction. It takes two input values, add them together, and outputs the result. So this is the hardware for the instruction fetch. So next we have this instruction decode or register fetch. So here you can see we have the decoder. So this is used for the instruction decoding. Okay. So next we have execute instruction and address calculation. So this here you can see we have this arithmetic logic unit, this adders, and this circuitry. So this is used for the instruction execution. So here basically we have the arithmetic logic unit, so that can basically perform the computation and all that tasks which are related to the instruction execution. So next we have this memory access. So here you can see we have this data memory, and in the end we have the write back results to the memory. So here you can see that we have the link for writing back the results. So this is the complete architecture for MIPS single cycle implementation. So in today's lecture, we discussed the computer architecture in details, and we discussed this MIPS microprocessor and the instruction format for the MIPS uh, processor, and how we can implement the MIPS single cycle. So this was all for today. So if you have any problem, please feel free to contact me via email. Thank you very much. See you next time.